we had seen oscillators introduction part. So in oscillators introduction, we have studied some very basics about oscillators, what is oscillator and how oscillators are working. So this is the basic block diagram of the oscillator, and we have also derived some conditions to achieve the amplification from the oscillator. So sorry, to achieve the oscillation from the oscillator. So what is that? So we have also did some case analysis. For example, this A beta is the loop gain. So this A is the gain of this amplifier stage, and beta is the gain of this feedback stage. So the multiplication of both gains must be equal to 1. For example, if it's less than 1, then the oscillation will die. So it will just go down, and we had seen some numerical examples based on the equation we have derived. And also if this A beta is greater than 1, then this amplification will just go higher and higher. So this is also not this is not what we want. So that is why it needs to fulfill this condition or satisfy this condition. A beta is equal to 1. Then we get sustained oscillation. It means we have a constant amplitude for every single cycle. So this is what we want from the oscillator. Okay, and also phase shift. Phase shift must be 0 degree or 360 degree. So it means whatever the phase you are giving in the input, and you are getting the same phase at the output. There is no phase change. And also I told you there is no input signal for the oscillator. There is an internal thermal noise. The thermal noise we can just amplify to certain amplitude, and then this because of this feedback, it will maintain this amplitude, and we will get again and again oscillations. So the voltage will go back and forth from plus to minus. So that is the property of oscillator. So now we will see different types of oscillators. What are different oscillators available and how it works? What is the circuit construction of each oscillator, and what is the operation of the circuit? So we will start one by one. First, we will see RC phase shift oscillator. Okay, so we have a possibility. Remember here in oscillator block diagram, we have two important stages. Any oscillator consists of two stages: amplifier stage and feedback stage. It's not a matter, it's RC or LC based oscillator. RC means what? This is a resistor and C is the capacitor. That is RC. Okay, and we know that this is the basic condition, and any oscillator must satisfy Barkhausen criterion, these two conditions. So it means A beta is equal to 1. It means the overall loop gain must be 1. And condition 2 is phase angle between input and output must be 0 degree or 360 degree. Phase difference between input and output should be equal to 0 degree or 360 degree. Okay, this we know that. So now what is special about RC phase shift oscillator? So in the amplifier stage, we can use either operational amplifier or transistors. So, but we can use, in this example, I already mentioned here, we will implement RC phase shift oscillator by using operational amplifier. Okay. Of course, you can also use the transistor instead of operational amplifier. What we want from here, we need amplification. So we know operational amplifier can be used for amplification. So we will use the operational amplifier in our circuit design. So in feedback stage, this is the feedback stage. If you use the combination of resistors and capacitors, let me take my pen. If you use the resistors and capacitors, then this circuit is called RC phase shift oscillator. So you should know the reason why we are calling this as RC phase shift. R and C and phase shift. What is the meaning of this phase shift? because we want either 0 degree or 360 degree phase shift. So if you use the inverting operational amplifier, you can naturally get 180 degree phase shift from this operational amplifier. So we have already studied about operational amplifier, how it works in inverting mode and non-inverting mode, right? So when you apply the input to the inverting mode, the minus, then you will get 180 degree phase shift at the output. And if this feedback network can also provide another 180 degree phase shift, then we will get 360 degree at the output. For example, so I have the thermal noise. The thermal noise is already having 180 degree phase shift. And then we are applying this to this amplifier. Amplifier is providing another 180 degree. So we get 360 degree. It means the input and output both are having same phase. Okay, so we are using resistor and capacitor combination in this feedback network. That is why we call this as a RC, and it provides a phase shift of 180 degree. So we call this as a RC phase shift oscillator. Okay, if we use inverting amplifier, operational amplifier, then it provides 180 degree phase shift that I already mentioned here. So another 180 degree phase shift we can get from RC feedback. So here we have 180 and here we have 180. So totally we get 360 degree. So now we will see RC network. RC, this is the resistor and this is the capacitor. I mentioned here RC network must provide here 180 degree phase shift. So if we talk about one single capacitor and single resistor, so I connect them together, I apply some kind of input voltage. So for example, I am applying here the V1. At the output, what I am getting? So I am getting 90 degree phase shift. So I am applying here like this, but here you can see the phase got changed. So it's starting from here. So 90 degree got out. So the 90 degree phase shift, and then we get at the output. So it means single RC network. I used only one component of capacitor and one component of resistor. I can get 90 degree phase shift. So in this case, what should I do? So if I put this kind of network together, like I can put one more capacitor and I can put one more resistor, then it can provide 90 plus 90, 180 degree phase shift, right? But the condition is, if you want to achieve the maximum phase shift, that is the 90 degree per pole or per stage, then the condition is R value should be really, really small, almost like 0. So here we have the R, but if you make this R value as 0, then the gain of this R and C combination will be 0. Then this is not really useful in the oscillator. So then we cannot really achieve the maximum phase shift of this RC network. So what is the solution for that? So this is what I mentioned here. In practice, we cannot make R value either too small or too large. That will affect the gain of this network. So, but we can design RC network that can give 60 degree phase shift. So if you want to get only 60 degree instead of 90 degree, then you can use some reasonable value to this resistor R. For example, here I used 100 mega ohms, but of course this is already 100 milliohms. This is kind of reasonable value. That value is also available practically. So each R and C network or one combination of resistor and capacitor can provide 60 degree in practical. So it means I need to connect this kind of combination to obtain 180 degree. So in that case, we need 3 RC network to obtain 180 degree phase shift. Okay, let us see the circuit. This is the circuit construction of RC phase shift oscillator. So this is very simple. If you just look at this part, This is one capacitor and one resistor. So I am putting this combination 3 times together in cascade mode or in series. So R and C, R and C, R and C, R and C. So each can provide 60 degree, 60 degree, 60 degree, and totally I get 180-degree phase shift. This is called a 3-stage phase lead network. Okay, so what I had done here, so I take the output of this RC 3-stage RC network and I am applying to the operational amplifier. So we know how the operational amplifier looks like. So this is the symbol of the operational amplifier. It has 2 input terminal, negative, that is the inverting input terminal. We are applying the input. The other terminal got grounded. Of course, every resistor or every RC network must be grounded the other side in order to complete the circuit and in order to have the current flow. Okay, so now we grounded this and we are applying the input to the other terminal, and definitely this operational amplifier will give 300. This will give another 180 degree, so we get 360 degree at the output. So this is the circuit construction, how it works, and then definitely we also take the fraction of output and feeding back to this RC network, and then the RC network is giving some output, and this output is given as the input to this operational amplifier. So operational amplifier output is given as the input to this RC network, and output of this RC network is given as the input to this operational amplifier. So this is what we want. So here you can see, so we are just making this closed loop. So we take the output here and then giving us the input to the feedback stage, that is the RC network, and then taking the output from this one, and then we are feeding back to this operational amplifier. So what is happening here? We need 3 RC network to obtain 180-degree phase shift. Each stage can provide 60-degree phase shift. An inverting operational amplifier can give another 180-degree. So now overall phase shift will be 360-degree. So we satisfy one condition of the Barkasian criterion. So as I mentioned, oscillator can work without any input. You see here, I am not applying any external input. If I construct this kind of circuit by using components, then this circuit will automatically produce oscillation. So remember, I put the gain of this operational amplifier as 29. I will talk about that in a while, but you should note down this point. Okay, so this circuit can work without any input. Thermal noise present in this RC network will act as an input, and it will be helping as an input to get oscillation at the output. Or we can say thermal noise is responsible for the oscillation. In many circuits, we do not really want thermal noise, but in the oscillator, we make advantage of this thermal noise, and we are using this to generate the oscillation. Let's see here. So naturally, thermal noise have multiple frequency components. So it means if this RC network produce some kind of thermal noise, so it may have several frequency components. So maybe this one that you can see that it's the one cycle, how long, and then you can see another cycle here. So you can always see one on time and one off time. For example, if this is the middle point, this is not a nice circuit. Okay, so let us say this one is one cycle, and then the another frequency will be, okay, I changed the amplitude here, but it doesn't matter the amplitude, but if you set up this gain, then there will be the same amplitude. So you have here, and then you have this, and then another one, the same amplitude. Here is the amplitude. So I have the same amplitude, but this signal is a little more wider. So the frequency is different. So this is one cycle, right? So this is a second cycle, and the third cycle will be maybe even more narrow. So thermal noise is a random noise. So it will have multiple frequency components inside. That's why we are using this RC network. RC network, what it will do, it's a kind of filter. So we have already studied about a low pass filter and high pass filters. They will only select certain frequency and then they will give as an input to this operational amplifier. So we will see here now. That's why filter circuit. So for example, this is the high pass filter combination. So high pass filter is we used in this feedback network. So it will give only one selective frequency with phase shift as an input to this operational amplifier. So what it means, it generates some kind of thermal noise. Thermal noise have multiple frequency components, but this will filter out and it will give only one constant frequency and constant amplitude at the output with 180-degree phase shift. So this is the meaning of this one. Okay, so it will select only one frequency and applying this to this operational amplifier. Then operational amplifier, it will do amplification and then it will give the output here. So remember, in the RC phase shift oscillator, we fix the resistor values. All the resistor values are fixed, but the capacitor values are varied to get sustained oscillations. So we can change the value of the capacitors because you are getting the oscillation at the output. So oscillation means what? That is maybe certain frequency. Maybe I'm getting like a 1 kilohertz oscillation at the output. 1 kilohertz oscillation at the output means what? So we are getting 1000 cycle. 1 kilohertz means this is like 1000 hertz, right? I am getting 1000 hertz per second at the output here. This just, you can imagine, this is like 1000 times at the output. So I want to change this to 2000 kilohertz or 2 kilohertz or 2000 hertz. So 2000 cycle per second. So how can I adjust that? So I can immediately change the capacitor values. Then I can change the frequency of the oscillation. So that is the purpose of keeping this resistor as a standard value, because if you change this one, then it will affect the phase shift. So we are changing only the capacitor values in order to obtain the phase shift. At the same time, we are also getting or we are also adjusting this frequency of the oscillation. So as a user, we can decide what kind of frequency we want by adjusting these values. Okay, and for this circuit, the standard value of beta is 1 divided by 29. So remember, what is the beta? Beta is the gain of the feedback stage. The feedback stage is here, this RC network. So we must get the gain 1 divided by 29. And so it means we have this gain of this operational amplifier should be 29. So here you know the formula, A beta is equal to 1. So if A is 29, then the beta value must be 1 divided by 29. Then only we can get the Barkasian criterion. So this 29 cancel, so we get the 1. So I am not deriving how to obtain this 1 divided by 29 or 29. So just to remember this, in RC phase shift oscillator, the gain of the operational amplifier is 29. The gain of this feedback network is 1 divided by 29. This is beta. So this is what we had seen in this one. So this is the beta feedback network, and this is the gain of the operational or any amplifier. It can be a transistor also. So, okay, so now you know this. And what else? What is the formula for frequency of oscillation? So frequency of oscillation is really depending upon the value of resistors and capacitors. We simply call this as a time constant. Maybe I used this term already in the filter design, time constant. This R and C value is, yeah. So here frequency of oscillation is equal to 1 divided by 2 pi RC. But here we should remember how many number of stages we are using in the feedback network. So this is for n number of RC networks. So For n number of RC networks, the formula is 1 divided by 2 pi RC square root of 2 times n. N is the number of RC networks. But in our circuit, how many stages or how many number of RC networks we have? We have 3-stage RC network. So you can, for example, then you can replace this n by this number 3. Then it will be 2 times 3, that is 6. So the frequency of oscillations of 3-stage RC phase shift oscillator is 1 divided by 2 pi RC square root of 6. This is the formula for 3-stage. Now let us say I am having a 4-stage network. What will be the formula? So I have to replace the n with a 4. Then it will be, instead of 6, it will be square root of 8. Okay, but in order to get the sustained oscillation, 3-stage RC network is good enough. But in science, we always have the standard formula to use in any condition. So in case if you need to use 6 stages or 9 stages, it's really depending upon the application. So you need to have the common formula to calculate the frequency of oscillation. And so remember here, the frequency is equal to 1 divided by 2 pi RC. So it means frequency and the RC value are inversely proportional. So it means when I increase the resistor value, the frequency of oscillation will be decreasing. It will be reduced. So because it's opposite, it's in the inversely proportional. So if I increase the R value, frequency of oscillation will decrease. And if I increase the C value, the same, frequency of oscillation will decrease. So, but if you want to increase this frequency of oscillation, then what should you do? So you have to decrease the resistor value. You have to decrease this C value, or you can do either of these. You can do either of these components, or you can do both components. If you decrease the resistor value, then frequency of oscillation will also increase. But we know that it's not a good strategy to touch the resistor value. So we better touch the capacitor value. So we just only reduce the capacitor value, then the frequency of oscillation will automatically increase here. So instead of 1000 Hertz, maybe you can get to 1200 Hertz or 2000 Hertz, or up to you. So you can calculate that value, the frequency, by using this formula. So by changing this value, you can just numerically easily calculate the frequency of oscillation. Okay, so now you know the formula of frequency of oscillation. That is F is equal to 1 divided by 2 pi RC. Same formula as the cutoff frequency of the filters. So we know high pass filter, low pass filter, band pass, band stop. So everywhere we use, this is the formula to calculate the cutoff frequency, right? Same here. So because we are using this RC network, high pass filter inside. So 1 divided by 2 pi RC square root of 2n. And we are using the same value for all these C and R. So that is, that's all about the RC phase shift oscillator. So what we had seen the circuit construction of this RC phase shift oscillator and how it works, and what is the formula of frequency of oscillation in this RC phase shift oscillator. So just remember the gain, this one, and this gain is 1 divided by 29. Then everything is okay. This is just to satisfy the Barkhausen criterion.